Welcome to our mathematics tutorial on multivariable calculus. Today, we'll explore three important and related topics: partial derivatives, tangent planes, and the chain rule for multivariable functions. These concepts are fundamental for understanding how functions of multiple variables behave, and they have numerous applications in physics, engineering, economics, and many other fields. Let's start with partial derivatives. When we work with functions of multiple variables like f of x and y, we often want to understand how the function changes when we vary just one variable while keeping the others constant. The partial derivative of f with respect to x, denoted as the partial of f over the partial of x, measures how f changes when x changes, but y is held constant. Similarly, the partial derivative of f with respect to y, denoted as the partial of f over the partial of y, measures how f changes when y changes but x is held constant. Let's look at an example of computing partial derivatives. Consider the function f of x, and y equals x squared times y plus 3x times e to the y minus sine of y. To compute the partial derivative with respect to x, we treat y as a constant and differentiate with respect to x using the rules from single variable calculus. First, the derivative of x squared times y with respect to x is 2x times y. The derivative of 3x times e to the y with respect to x is just 3 times e to the y, since e to the y is constant. And the derivative of negative sine of y with respect to x is 0, since it only contains y. So, the partial derivative of f with respect to x equals 2xy plus 3e to the y. Similarly, to compute the partial derivative with respect to y, we treat x as a constant. The derivative of x squared times y with respect to y is just x squared. The derivative of 3x times e to the y with respect to y is 3x times e to the y. And the derivative of negative sine of y with respect to y is negative cosine of y. So, the partial derivative of f with respect to y equals x squared plus 3x times e to the y minus cosine of y. Now, let's move on to tangent planes. A tangent plane to a surface z equals f of x, and y at a point is the plane that best approximates the surface near that point. The equation of the tangent plane at a point x naught, y naught, z naught, where z naught equals f of x naught, y naught, is z minus c naught equals the partial of f with respect to x evaluated at x naught, y naught, times x minus x naught, plus the partial of f with respect to y evaluated at x naught, y naught times y minus y naught. This is analogous to the tangent line in single variable calculus, but now we're working in 3 dimensions. The tangent plane touches the surface at exactly one point and provides a linear approximation of the surface near that point. Let's work through an example of finding a tangent plane. Consider our function f of x. Y equals x squared times y plus 3x times e to the y minus sine of y. We want to find the tangent plane at the point 1, 0. Step 1. First, we need to find z naught by evaluating the function at x equals 1 and y equals 0. F of 1, 0 equals 1 squared times 0 plus 3 times 1 times e to the 0 minus sine of 0, which equals 0 plus 3 times 1 minus 0, which equals 3. So our point is 1, 0, 3. Step 2. We need the partial derivatives evaluated at 1, 0. We already calculated that the partial of f with respect to x equals 2xy plus 3e to the y. Plugging in x equals 1 and y equals 0, we get 2 times 1 times 0 plus 3 times e to the 0, which equals 3. Similarly, the partial of f with respect to y equals x squared plus 3x times e to the y plus cosine of y. At the point 1, 0, this gives us 1 squared plus 3 times 1 times e to the 0 plus cosine of 0, which equals 1 plus 3 plus 1, which equals 5. Step 3. Using the formula for the tangent plane, we have z minus 3 equals 3 times x minus 1 plus 5 times y minus 0, which simplifies to z minus 3 equals 3x minus 3 plus 5y, or z equals 3x plus 5y. This is the equation of our tangent plane at the point 1, 0, 3 on the surface. Finally, let's discuss the chain rule for multivariable functions. The chain rule tells us how to compute the derivative of a composite function. In the multivariable setting, it gets more complex, but follows the same fundamental idea. If z equals f of x and y, and both x and y depend on t, such that x equals x of t, and y equals y of t, then the derivative of z with respect to t is dz over dt equals the partial of f with respect to x times dx over dt plus the partial of f with respect to y times dy over dt. This formula tells us that the rate of change of z with respect to t can be broken down into two components: how z changes with x times how x changes with t, plus how z changes with y times how y changes with t. Let's work through an example of the chain rule. Consider the function f of x, y equals x squared times y. Let's say x equals t squared and y equals sine of t. We want to find dz over dt at a general value of t. Step 1. First, we compute the partial derivatives of f. The partial of f with respect to x equals 2xy. The partial of f with respect to y equals x squared. Step 2. Next, we compute the derivatives of x and y with respect to t. The derivative of x equals t squared with respect to t is 2t. The derivative of y equals sine of t with respect to t is cosine of t. Step 3. Now, we apply the chain rule formula. dz over dt equals the partial of f with respect to x times dx over dt plus the partial of f with respect to y times dy over dt. Substituting our results, we get dz over dt equals 2xy times 2t plus x squared times cosine of t. Step 4. Finally, we substitute x equals t squared and y equals sine of t into our expression. dz over dt equals 2 times t squared times sine of t times 2t plus t to the fourth times cosine of t, which simplifies to 4t cubed times sine of t plus t to the fourth times cosine of t. This is our final expression for dz over dt, which tells us the rate of change of the composite function with respect to t. To summarize what we've learned today, partial derivatives allow us to understand how a function changes with respect to one variable while keeping others constant. Tangent planes use these partial derivatives to create a linear approximation of a surface at a specific point. The chain rule extends to multivariable functions, allowing us to compute the derivative of a composite function by combining partial derivatives with the derivatives of the inner functions. These concepts are fundamental to multivariable calculus and have numerous applications in physics, engineering, economics, and many other fields. Thank you for watching. I hope this video has helped you better understand these important calculus concepts.